So the final question in this topic, in fact the final question in the module, is capturing the principles of conservation of momentum. So we're no longer applying external forces or moments. Clearly if we're thinking angular we'd be thinking moments. We're thinking whatever's there at the start is there at the end. And this is nicely captured in this example where we've got a 10 kilogram wheel. We're told the inertia. We could have calculated it if we'd known the radius of gyration, but we've been given it, which is nice. It rolls without slipping, so we know that there's no losses there. Doesn't rebound when it hits the little step at A. And we want to know the minimum velocity Vg that the wheel has to have to roll over A and then come to rest, because that's what it needs. If it's just got the minimum velocity, it's going to roll up onto A and stop. So this is capturing the principle of conservation of momentum. Okay, so when we think of conservation of momentum, we're saying, well, our angular momentum at the start is equal to our angular momentum at the end. That's conservation of momentum. If we drew those same sorts of diagrams as we'd drawn earlier, so we're going to have one where it's just hitting the step, so the start of the movement, if you like. There's some rotation, so there's an I, G, omega at the start. There's point G. Very, very similar diagram to earlier. The only slight difference here is where the distance of rotation. So in order to calculate the angular momentum, so the angular component that this MVG, that this linear momentum gives, we need the perpendicular distance. A bit like when we're doing moments, we need the perpendicular distance. So that's going to be the radius. Well, the radius of the wheel is 0.2 minus the height of the step. And the height of the step from the question is 0.03. That will give me the distance between A and G, which will be the perpendicular distance that I need in the next step of my my calculation. We then think about all of the forces that are acting to cause a change in momentum. Anything that could change an impulse. Sorry, anything that could cause an impulse, change in momentum. So there's going to be a contact force with the step. It's going to be at an angle, because it's not going to be a straight contact, and it's going to be a distance away from the centre, and my weight is going to be 10 times 9.81, and that's all going to be, because this is an impulse diagram, times t. And that's going to come out with a new angular momentum where we're just rotating about the step. So this is just where we're rotating. If you imagine it's just lifting off the ground. We know now the distance between G and A, because that's the radius. And it's still going to be rotating, but it could be going at a different speed. Okay, so it's in the purple diagram, it's rolling along the ground. In the orange diagram, it's hit the step, and we're thinking about the forces that are being applied over the time that it's in contact. And then in the green diagram, it's just starting to lift off the ground and roll around that step, but it's in the first stage of that transition. So if we're thinking conservation of momentum, then we're saying whatever there was at the start in the purple diagram is there at the end in the green diagram. So we can say, well, remembering there's two components to angular momentum in the purple and in the green. There's the bit that's already there, ig omega, and there's the piece created by the linear, the mvg, being a distance away from the pivot point. So we've got 0.2 minus 0.03. We've got the distance away times by mvg. M is 10. Vg we do not know. The inertia is 0.156. And omega 1 we don't know. We're going to skip over the orange diagram because we're saying, well, momentum is conserved in this. So in our green diagram, we're going to have exactly the same sorts of calculations, but this time it's 0.2, G is 0.2 meters away from A because it's just lifting off the ground. The distance between G and the point it's rotating about, the tangential distance, sorry, perpendicular distance is now 0.2 times by 10 times by Vg2. We know our inertia again, 0.156 omega 2. We also know V equals omega r. So omega equals V over r, which equals V over 0.2, which equals 5V. So we can substitute that into our equation. So we can get rid of our 0.156s, and we can say, so we could say 0.1. Let me rewrite it underneath. So we can say 0.0. Sorry, no, it's not. 0.2 minus 0.03 by 10 by Vg1 plus 0.156 5Vg1 equals 0.2 by 10 by Vg2 plus 0.156 5Vg2. We've now got Vg1 and Vg2, so we've still got two terms, but we can simplify it a little bit. So we can say 0.892 Vg1, that's just bugging everything in a calculator, equals Vg2. So I've simplified everything down. Now you may remember back when we did the particle impulse and momentum questions, when we were thinking about conservation, we didn't just stick in the impulse and momentum space. We can also think about energy and energy transfers. And what we can do there is we can form a second equation. That second equation can then help us find some of these unknown terms, because clearly here we've got, in our purple and green diagram, purple and green equation, we've got two unknowns and only one equation. So if we go into conservation of energy now, we can say, well, let's think about a slightly a different scenario, not much difference, but the next stage of the journey, if you like. So I'm going to go with green. I'm going to draw some more pictures. I've picked green because this is meant to represent the same green stage, so stage 2 of the journey, where it's just rotating about the step, the lip. Let's put the datum there and I'll extend that line. And then we're going to have a second. This is maybe not as well drawn. No, it's not well drawn at all. Because my step wants to be underneath, doesn't it? So in that second image, the pink image, which I managed to 0.03, the G, the centre of gravity, has been lifted up as it's come off the floor to 0.03 metres above where it was before, because it's the height of the step. And we want to know the velocity to just roll around the step. That's what we've been asked for. It was the initial velocity to just roll around the step. If it's just going to roll around the step and then stop, then we know the kinetic energy at the end. So what we can say is our kinetic energy and our potential energy, and I'm saying it position 2 because if you remember, position 1 is our purple position where we're running towards the step, we're just impacting the step. The green stage 2, we're rolling around the step, and then our pink stage here, stage 3, we're stopped on top of the step. And that shouldn't say plus, that should say equals. So for the for this final stage, we're talking about the energy conservation, but obviously the commonality, the common piece is going to be stage 2, because stage 2 is common to both of those, and we can use the two equations to work out the unknown.
Playing from
So substituting in some values for our kinetic energy and our potential energy. Well, from our green diagram, we know we're going to have a half times by the mass times by Vg2 squared. So that's our linear kinetic energy, translational kinetic energy. We've also got half times by 0.156, so half Ig omega 2 squared. So that's our rotational kinetic energy, so both of those components. In terms of potential energy, I've drawn the datum straight through G. So in the green picture, it's going straight through G, so there is no potential energy. So let me put that one as rotational kinetic translational kinetic. Both of those make up T2. That's just V2, potential energy. In our pink diagram, well, our kinetic energy, we've asked it to stop on the step, so there's no kinetic energy. That's what we're calculating. And the potential energy is going to be the mass times by gravity times by the change in height, 0.03, which I've tried to indicate badly, possibly, on my diagram. So the two things we don't know in there, we don't know V, we don't know omega. We do know, though, that omega 2 equals 5 Vg2, because we've worked that out up here. It's the form of the pink equation that is now at the top of the screen, because we know that relationship V equals omega r. Keeps coming through. So we can substitute that in. So we can say, okay, I can get rid of one of these values, and I can say, Vg2 squared plus half times 0.156, and then rather than omega squared, I'm going to have 5Vg2 squared is equal to 10 times 9.81 times by 0.03. So I've now only got VG2 in the equation, so I can say I can find VG2. Unfortunately, I haven't got a number for that. I will go away and work that out and write it in. But I can substitute that number when I find it back into my conservation of momentum, the first stage. So I can go back into just here, and I can get myself VG1 back out. So VG1, which I was writing in purple, so I'll go back to purple. So VG1 can then be found as equaling 0.729. That's a terrible 2 meters per second. So if the wheel rolls with a velocity of 0.729 meters per second, it will hit the step at A, roll onto it, and come to rest. That's what that's showing. And I just need to go away and work out that one number to go in the yellow highlight for completeness for your notes. Just for completeness, that final value for VG2 is 0.651 if you're trying to calculate or check as you go along, check the stages. But the final answer, it was actually after the final term, VG1, that minimum velocity, 0.729.